Organometallic compounds. In all the compounds that we have seen so far, say for example alkyl halides, alcohols, ethers, and epoxides, we see that the carbon is connected to a more electronegative atom. So in which case, this carbon is going to act as an electrophile where the nucleophile can go and attack this electrophile and a reaction could happen. But if you want this carbon to act as a nucleophile, then it should be connected to a more electropositive atom. Say for example, if this carbon is connected to a metal which is more electropositive than carbon, then it can react as a nucleophile. So this would be more electropositive than carbon, and therefore this is going to behave as a nucleophile. So in which case this nucleophile can react with the electrophile for the reaction to take place. So these compounds where there is a bond between carbon and the metal are called as organometallic compounds. A wide variety of metals can be attached to carbon to form organometallic compounds. Here are some examples. Out of these, organomagnesium compounds and organolithium compounds are the two most common organometallic compounds, and along with that we can also add organocuprates. Let's see how the organometallic compounds are named. They are named simply by adding the alkyl group in front of the metal. Say for example, here we have totally 4 carbons in the alkyl chain, and therefore this should be butyl, right, for the alkyl part, and you have the metal lithium here, and therefore this should be butyl lithium. And the next compound is an example for a Grignard reagent. This is organomagnesium bromide, and to be more specific, this is called as ethyl magnesium bromide. And the third example, this is a propyl group, but we have 2 of these units. So this would be dipropyl cadmium. And we have ethyl group here. There are 4 ethyl groups here. And this would be tetraethyl lead. Synthesis of organometallic compounds. Organolithium compounds are generally prepared by adding lithium to an alkyl halide in a nonpolar solvent such as hexane. For example, when you take 1-bromobutane and react it with lithium in the presence of hexane or other nonpolar solvents, you will be able to get butyl lithium. And you can also conduct exactly the same reaction with aryl halides. For the synthesis of organomagnesium compounds, you can take alkyl halide or aryl halides or vinyl halides and react it with magnesium shavings in the presence of ether as a solvent. Usually diethyl ether is used, or you can use THF also. In this reaction, the magnesium is going to get incorporated between the carbon and the halogen bonds. The magnesium is going to go in here. Okay, and that's how you will form the organomagnesium compounds. Here the solvent plays a very crucial role in the formation of the Grignard reagent, because you can see the magnesium has got only 4 electrons. It needs to have a total of 8 electrons in order to complete the octet, for which it will take the electrons, the 4 electrons from the oxygen present in ether. Right? These oxygens are going to donate these electrons, and that's how the metal is coordinated now. Because now these solvent molecules are surrounding the metal is now protected from being coated, which would make it unreactive. And it is also extremely important that we do these reactions under anhydrous conditions. These compounds, organomagnesium compounds, are also called as Grignard reagents, named after the scientist who discovered it, Victor Grignard. So these compounds, organometallic compounds, organomagnesium and organolithium compounds, are going to react as if they were carbanions, because here the carbon is coordinated with a more electropositive atom. Okay, in each case we do have a metal that is coordinated with carbon, and because of which this carbon will behave as a nucleophile. One of the important reactivities of these organometallic compounds is that it will react with the proton. For example, when you take methyl magnesium bromide, we know that this part right here is going to act as a nucleophile. So this is going to have a negative charge, which will go and abstract this hydrogen from the water molecule. In the same way, it can abstract hydrogen from alcohol, ammonia, amine, and even an alkyne to form alkane in each one of these cases. And that is the reason why we use strictly anhydrous conditions when we synthesize organomagnesium compounds and organolithium compounds. Taking advantage of this, we can also synthesize deuterated hydrocarbon. Say, for example, the first part is the synthesis of Grignard reagent, where you react the alkyl halide with magnesium shavings in the presence of THF as a solvent, and you're going to convert this into Grignard reagent. Once it is converted into Grignard reagent, depending upon what you want, like if you want to convert it into an alkane, then you can react simply with water. But if you want to convert it into a deuterated alkane, then in that case you have to use D2O, okay, where this carbon with a negative charge on it will go and attack the deuterium, so the deuterium can get added to it. When it comes to the reactivity of the organometallic compounds, it's definitely going to depend on the polarity of the carbon metal bond. Say, for example, greater the polarity of this bond, greater would be the reactivity of the organometallic compound. Okay, so polarity of the bond is going to directly proportional to the reactivity of the organometallic compound. Let's compare organomagnesium compound with organolithium compound. So when we take organomagnesium compound, we are having a bond between carbon and magnesium. When it comes to organolithium compound, we have a bond between carbon and lithium. Let's find the electronegativity difference between these two atoms. Okay, so we have magnesium here with 1.2, and we know for carbon it's 2.5, and we subtract from each other, it would be 1.3. And similarly, if we take lithium, lithium has an electronegativity of 1.0, and therefore this is going to be 1.5. So we can see that the electronegativity difference between carbon and lithium is more when compared to the electronegativity difference between carbon and magnesium, and therefore this bond right here is more polar and this is comparatively less polar, and therefore the organolithium compounds are more reactive compared to the organomagnesium compounds. So this is less reactive, whereas the organolithium compounds are more reactive. Organometallic compounds can undergo transmetylation if a less polar carbon-metal bond will be formed. For example, when you take an organometallic compound and react it with another metal salt, if that metal is more electronegative, then the transmetylation occurs. Okay, let's take this scenario, reacting ethyl magnesium bromide with cadmium chloride. Here, let's find out the polarity of the two bonds. The electronegativity of magnesium is 1.2, and for cadmium it is 1.5, right? So this is obviously more electronegative. This is the bond that is actually present in organomagnesium chloride, and this is the bond that is present in this organometallic compound, diethyl cadmium. Now let's find the polarity of this these bonds right here. We already calculated it to be 1.3, and here it would be 2.5 minus 1.5, that would be equivalent to 1.0. Now between these two bonds, which one is polar? Obviously this is polar and this is less polar, like comparatively less polar. So an organometallic compound which has a more polar bond can be converted into another organometallic compound which has a less polar bond. So this process where the metal has been exchanged is called as transmetylation. Here is one more example for transmetylation where a more reactive organolithium compound has been converted into a comparatively less reactive organocuprate. Okay, so this one right here is an organocuprate. So let's find out the relative polarity of these bonds. Okay, so we have CCU bond. We have talked earlier that the electronegativity difference between this is going to be 1.5, right? But here it would be, see, 2.5, and for copper, the electronegativity is 1.8, and therefore this is going to be 0.7. So you can see that this is going to be a more polar bond, and therefore this is more reactive, and this one is a less polar bond, and this is less reactive, and therefore this reaction is possible. So when you react an organolithium compound with cuprous iodide, you can get the organocuprate. The organocuprates are also called as Gilman reagents. With the use of organometallic compounds, it's possible to synthesize new carbon-carbon single bond. And this reaction where you synthesize new carbon-carbon single bond using organometallic compounds is called as coupling reaction. Here is one such example of the coupling reaction. Here we have organocuprate, and here we have an alkyl halide. So with an exception of alkyl fluoride, the rest of the alkyl halides can undergo this reaction. When organocuprate is reacted with alkyl halide, what's going to happen here is the halogen here will be replaced by the alkyl group in the organocuprate. So you can see there are 4 carbons here in the alkyl halide, and here we have 3 carbons just in one part of the one alkyl group, and therefore altogether it would be 4 plus 3 will be totally 7 carbons in the resulting compound, right? And you can see here is the new carbon-carbon single bond that is formed. Okay, and the other alkyl group from here is going to get coordinated with copper. So this reaction, where we take advantage of the organometallic compound to synthesize new carbon-carbon single bond, is called as coupling reaction. And we can also do this coupling reaction with vinyl halides and as well as aryl halides, where you can see again where the halogen is present, it has been conveniently replaced by the alkyl group or the alkenyl group from the organocuprates. So instead of bromine, we do have this ethyl group, and instead of this iodine right here, we do have this vinyl group. We know that the vinyl halides and the aryl halides do not undergo any SN2 reactions, where these halogens cannot be replaced by other nucleophiles. But we can take use of these coupling reactions so as to convert them to useful compounds by substituting these halogens with other groups. This coupling reaction, which is basically a substitution reaction, is stereospecific. If you start with cis, you'll only get cis. And if you start with trans, you'll only get trans. So basically, the configuration of the double bond is retained in the product. And organocuprates can also replace halogens in compounds that contain other functional groups. For example, here we have a ketone, halo-substituted ketone, and this halogen can be conveniently replaced by this methyl group from the organocuprate.